Alright, we're back. I know I've been saying this for I don't even know how long, but I really should get like an external mic for real, but I just don't care to. I'm going to. I just finished doing my Spanish. I usually don't do my Spanish stuff on stream, but I just finished doing my Spanish, and I'm actually going to do a bit of geometry before I start differential geometry because I think it'll help, even though it's going to be super basic, but it doesn't matter. And yeah, I think I'll be able to. Wait, let me make sure my thing is. Alright, let me see how I'm gonna do this. Don't I have another view? What if I put this over here? Like this. Okay. I think this. Okay, no, let me scoot this way. Alright. And then I'm going to do this. Oh, shoot. Okay, wait. Bet. Okay. I think that works. Alright. Follow me. But, we're gonna test this out. Most of my progress is in Spanish, but I just learned about this. Can you? Oh, really? It connected to the desktop audio. That's kind of crazy. Oh, I won't. I'll turn that down. I'm not gonna. Oh, shoot. Oh, it like really connected for real. I didn't think it would. Oh, that makes sense. Okay. That's fine. I'll just do that. All right. Oof. We're starting off tough. 2 plus 1 is 3. 3 plus 1 is 4. Oh my gosh. Let me stop. Okay. This might be redundant. I'm not gonna lie. Okay. This might be extra. I low-key still want to do it though. Mental math. After this one, I'll move up though. 0, 3, 6. Oh shoot. Whoopsie. 9, 10. This is very elementary. What's 3 inches more than 6? Oh. Do you know what's so crazy though? I actually struggle with these. Like, I struggle bad with math word problems. It's actually kind of crazy, but I need to get better at them because that's literally what the Putnam exam is. That's what high-level mathematics is in general, just high-level word problems. Yeah, this is very elementary. Oopsie. Okay, I think I can skip. Can I not? Wait, so I can jump, but I can't. Wait. Really? So I can jump. So I can jump to the. Oh, shoot. Hold on. My dog's about to act the fool. I don't want to talk about it. I don't want to talk about it. That's so funny. I'm just gonna stop there. I obviously need to do more of that then, huh? That's so funny. It's funny, but it's not. But it's funny. Holy crap. Um I when it said area, I was interpreting it as a triangle. Wait, no, flip that. When it said triangle, I was interpreting it as area. So I wasn't dividing by 2, and it was screwing me over. It's fine. Um I'm going to do some work now. So that's beyond me.
At Harvey Mudd College, real analysis is an exciting subject. It is one of the first
exciting journey into the world of differential geometry, the branch of mathematics that blends the elegance of geometry with the power of calculus to study the shapes, curves, and surfaces. This complete course on differential geometry is a step-by-step journey into one of the most fascinating branches of mathematics. From understanding the simplest curves to diving into the geometry of higher dimensional spaces, this course will guide you through the very essential topics in differential geometry. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to the first lesson in learning differential geometry. Well, before we go into the curves and surfaces and twists and turns, let us first understand that what is a differential geometry. If I go by the definition, then it is very simple. It is a branch of mathematics that deals with smooth shapes, smooth spaces, otherwise known as smooth manifolds. Now, each of these terms, smooth and smooth spaces and manifolds, have a different meaning. Then you can ask me that something which is not smooth, that means rough or something like that, will it not be dealt into differential geometry? We will answer the question later. But first of all, let us see that the word differential geometry comprises of the first word, which is differential, which means using calculus and using differential and integral. And in order to study surfaces and manifolds, obviously these are local, not global in nature. The question is that what is the mathematics branch which deals with global curvature or global nature of these surfaces? That is called topology, which is out of the scope of today's video. However, differential means that we are using calculus to understand shapes and sizes, which are something very local. Going to the next phase, which is called geometry. Obviously, these have geometric properties, and we start with Euclidean, then we move into non-Euclidean, studies the different shapes of shapes and sizes. So here is a quick summary that a differential geometry comprising of two words is actually reflecting the core idea of using differential calculus in order to study and analyze different types of shapes and sizes, which are smooth and which have got different types of, which are something very local. proper of using differential calculus in order to study and analyze different types of shapes and sizes which are smooth and which have got different types of twists and turns. From here, we get a better understanding of the subject. So differential actually means that we are using something which is to differentiate or to understand the infinitesimal differences, which are differential distances, concepts like that using calculus. And when we talk of geometry, then the surface will have where all the physics or all the things which are twisting and turning taking place. And using calculus means that we are not using here a flat space. We are doing with some twists and turns and shapes and sizes. So the underlying structure of the entire physics of the mathematics depends on this, which is geometry. Now, differential geometry is called so. Why? Because it's a branch of mathematics that study the geometric properties in understanding using local differential calculus. So here we understand these things which we will essentially take up in the due course of time of this entire series: derivatives, local analysis, connections, and water tangent spaces. Now we understand that geometry is required because we take into account shapes and sizes and curves. But question is that why do we need to use calculus? Why calculus? Why not anything other than mathematics? Let us understand why you need calculus to understand differential geometry into this part of the video. Now, if I show you certain figures, for example, calculus, particularly differential calculus, uses this type of objects which are, have got shapes, curvature, lengths in order to calculate this. So we need a calculus. So applying the rules of calculus on what is called a manifold, although manifold has got a very technical definition, we will take it up later, but this is why we need the calculus. Also, in order to find the derivatives, finding slopes, we need them. Integrals, finding the area and volumes, how these things changes. We will see differential area, differential volume, how these things happen. And calculus also helps to analyze the properties of curves such as curvature, torsion, and arc length together. We will also see, which is a very important concept, calculating geodesics, which are the straightest possible path a particle travels in a curved space, and something which is called a tangent plane, just kisses the boundary, kisses the surface, which is called the tangent plane, where all the planes are tangent. So all of this requires calculus. As you can see, small infinitesimal changes, distances, integral volume, particle moving along in geodesics, these are required. Now, if I take this kind of a diagram where you see these lines are converging, it means a positive curvature. These lines neither converge nor diverges, it remains straight, so it is a zero curvature. And here the lines are diverging, so it is a negative curvature. So all these things are basically required to do calculus. So each of this object, the hyperboloid, the cylinder, and the sphere, you can see they have small boxes. And these boxes are where we are dividing into infinite small distances. So if I take out, zoom out one of these curved surfaces, and I start differentiating these into small boxes, we get something like a differential area, which is calculated by dy by dx. So we are applying the rules of calculus on this type of a manifold, a hyperboloid, a sphere, and a cylinder in order to calculate that. Also, what an important point comes up is that all these things, you can see these yellow boxes, they should look equally, I would say, locally Euclidean. And when you zoom in and zoom, it becomes locally Euclidean. But remember, these are not Euclidean spaces. These are curved spaces. But manifold, the definition itself says that a manifold is a surface which should look like a locally Euclidean. We will take up Euclidean surfaces or Euclidean part manifold later, but this is how what justifies the need of calculus. So we need something which we call smoothness, because it is a function, is a property measured by continuous derivatives. And continuous derivative means that the function is differentiable and its derivative is a continuous function. So if f is differentiable, then f prime, we call it as continuous. So this is a differentiable function. This is again, and this is not a continuous. As you can see, there is a break. So if I take this kind of a shape and I try to make small boxes, that means I'm continuously differentiating them. We call it as a differentiable structure. a structure which can be divided. This is a differentiable structure, but this part of the surface, as you can see, this is smooth, so it is called a continuous derivative. So this actually justifies our question that why we need calculus. These are the reasons we need calculus. Now we come to a fundamental question through which we make the first baby step in the world of differential geometry is what is a curve? Now, if I ask you a question that what is a curve, you might say that you can give a simple example. For example, you might give a straight line, y minus 2x equals to 1, although it is not curved. Or you can say it can be a kind of a parabola, or it can be a circle. So all these curves, as you can see, actually can be described by means of a Cartesian equation, which is this. And this equation is very important. This is the first step and requires a detailed understanding for learning differential geometry. So as we see that all these curves are described by this Cartesian equation, f of x comma y equals to c. So here what we are trying to say, this is again, this equation, let me first tell you, it's a very generic way of representing curves in the Cartesian plane. So in each of these three cases, as you can see here, I would say the straight line, the parabola, and the circle, this format is maintained by expressing the equation into as a function f of x comma y, where we will see now further what it is. So here what happens is that the equation defines the relationship between x and y coordinates. And for example, we can take a straight line. So if f of x ax plus by plus d equals to 0, here you will see that f of x comma y is equal to ax plus by plus d, and c is basically 0, that is a constant. So if we take the straight line, for example, this as an example, then from here what we can see, we get a graph like this. And f of x, so f of x comma y, which we are talking about, comes over here, and this is x plus y equals to 3, and c is equals to constant. So what does it mean actually? This means that the straight line consists of all points x comma y, where x plus y minus 3 equal to 0 is actually maintained in the format. So x plus y minus 3 equal to 0 is being maintained. Going to the next example, which is a parabola, the equation of a parabola typically is a quadratic equation, and it takes this kind of a shape. So here again, we can say that f of x comma y equals to y minus ax square minus bx minus c, and again c equals to 0. So this f of x y, which we started telling that this is a very important equation. So this, for example, if you take f y equal to x squared, it would give this is a kind of just an understanding of how the parabola looks like. So f of x comma y would be equal to y minus x squared, and c again would be 0. From this equation, what we can understand is this means that the parabola is a set of all points x comma y, where y minus x squared equal to 0 again maintains or preserves the format f of x comma y equals to c. And if a parabola, which I have not mentioned over here, shifts, for instance, y minus x squared equals to 1, it could be written in a different kind of an equation. The third example is that of a circle. So the equation of a circle is something like this. And here again, f of x comma y can be written as this. So I have taken the explicit and the implicit, which I'm going to explain later. So it can be written as this, and again c equals to 0. So if I take an example of this, it would plot a kind of a circle like this with a radius of 2. And here again, f of x comma y equal to x squared plus y squared, c equals to 2. And this means that again, the equation is still in the form f of x y equals to c, and where the constant c determines actually the radius of the circle. So whatever be the circle, it goes ahead. So from these three equations, which we have just seen, that of a parabola, and before that we have seen a straight line, a parabola, and a circle, we can actually now tell that if I take this equation, the general observation is that the function f of x comma y actually encodes, or it holds the entire shape of the geometric structure of whatever the curve that we are watching. If we take c, the constant, this may vary. It would represent a slope-intercept conditions, the focus of the parabola, or the radius of the circle, whatever it happens. So this format works very well because it generalizes the way we describe a locus of points in the planes algebraically, and the curve is a simple collection of these points. Now, you might have a question, which is this: is there any other geometric shapes and curves which actually can be expressed in this general format? And the answer is a big yes. For example, if you take an ellipse. So the ellipse equation is something like this. Here again, f of x comma y can be written as this, and we have taken c equals to 1. So from here, what we can see again is a hyperbola. So from this equation, let me tell you that in the ellipse, what it says is that the set of all points x comma y, where the sum of the distances from the two foci is constant. That is why f of x comma y equals to c is clearly maintained. If you take a hyperbola, the equation looks something like this, right? X minus f of x, yeah. So from here again, we can write the equation as this one: x minus h square by a square, and so on, y minus square, this one. And here again, what we can say is that we can get into another, okay, also what we can say that this describes all the set of points where the difference of the distances from the two is fixed, and again the equation maintains f of x comma y equals to c. We can also see exponential curves, which again takes this kind of a shape. And here what happens is f of x comma y equal to y equals to a e to the power kx. So there can be certain other equations like logarithmic, conic sections, level curves of multivariable functions, and so on. So yes, with this equation, we can express other curves. Now, the big question is that f of x comma y equals to c, we are constantly dealing with this equation. But what is the name of this equation? What is this equation called? Now, that is what we are going to deal in the next part of the video. This is what is called an implicit function, a very important concept for understanding differential geometry. Now, if I take by the definition, basically an implicit function is one where the relation between x and y is given indirectly, often in a single equation where we do not take out y. So here is the definition. Often in a single equation where y is not explicitly solved in terms of x. Let us see one example. For example, if I take this one, which you can understand as a circle, here you can see the equation represents a circle with radius 1 centered at the origin, and y is isolated. Whereas if I take this kind of an equation, ellipse, for example, x squared and so on, I'm not repeating. Here, this equation represents, again, y is not explicitly, I would say, written. So this is how it is. Now, if I now take an explicit equation, which is the opposite of implicit, the equation would look something like this. So let me tell you, an explicit equation is one where y or any other variable, a, b, c, d, whatever it is directly expressed as a function of x. You can compute y explicitly at any given x. So this is called an explicit equation. Starting with the same circle, even in the explicit form, we can take out this y we are computing now, plus minus y square root of y minus x squared. So this represents actually the upper and the lower semicircles if it is plotted. And if you take the hyperbola ellipse equation, for example, then again what we can do is that we can calculate y. So this is the explicit form, or where it is the ellipses upper and the lower halves are being expressed. So this is what is called the explicit and implicit, and what we are doing is that we are actually showing you the implicit function. Now, this implicit function, which we denote in differential geometry as we deal with more complexities, can be represented as this. This is what is called a set notation. So this describes a set of all points x comma y in the two-dimensional plane that satisfy the condition of f of x equals to c, comma y equals to c. So it actually defines a curve in the plane R2. And this is a kind of a set notation. Let me explain you what are the components of that so that you get a better understanding. So this part of the equation means that the points x comma y lies in a two-dimensional space that means real numbers in both x and y. If I take this part of the equation, it means that this is a kind of a condition. You can say it is a constraint or condition that the points must satisfy to belong to the set. And c obviously is the constant. So here, as you can see, is a constant. So the function f of x comma y is a scalar function of two variables, often representing something. It can be a height or a distance or any other property. And c is a constant, and we are looking for all points of x comma y where the function f of x comma y has the value of c. Now, if I want to express this set notation, which is a very convenient way in using proofs in differential geometry, what we can do is that we can take an example of a circle, which is this one, and this represents the same kind of equation. So it shows that this represents a circle of radius 1. Centered at the origin. We can take an example of an ellipse. Similarly, this represents an ellipse with a semi-major axis A and the semi-minor axis as B. And an example of an hyperbola would show something like this, and this actually shows an hyperbola. Now we come back to the original equation which we started learning, and I will explain you the parts. So first one is the C. You can imagine it to be a container, a kind of a holder, where all the points that satisfy the given equation. If I take this part, it indicates that we are dealing with ordered pair of numbers, and each pair represents a point in a two-dimensional space. This one actually shows that it's pairs with x comma y belonging to the set of all numbers. And this is, as I told you, this horizontal bar, the vertical bar, is actually something which is given. It introduces a condition such that given that or so. And this part of the equation says that for a point x comma y to be in the set C, the function f evaluated at that point must be equal to a specific value or a constant, which is C. So we will use this set notation often and on again in different areas of differential geometry, but this is just to give you an idea of the components so that we can plug in the other values in due course of time and you won't face any problem. So this describes a curve as a level set of the function f of x comma y. What is a level set? That requires an understanding. We will come to that. That later. Now, the biggest question is that we all understand implicit, explicit, set notation, but what is the use? I mean to say, if you're learning differential geometry, why we are doing this? Now, there are several usage. Among them, the first part is that it actually helps to describe certain closed curves. Now, there are open and closed curves. We will deal with that later. And multi-valued relationships. It is also significant because it is very compact. You don't really need to write a lot, and the equation is closely tied. So we will see when we will deal with level maps how the geographical contour maps, etc., are being described with those. It is also used in geometry because it is used to define curves and regions and allows compact representation of conics, polygons, and other shapes. Calculus, obviously, partial derivatives. Implicit differentiation is used to find the slopes, and in physics, to field lines and equipotential surfaces. These are used to represent, using the implicit equation. So all of these are very, very important. Now, apart from that, something also comes up very important as we turn the pages is that it gives you an intuitive grasp of geometrical objects, obviously, because in order to study the curves and surfaces, you have to learn all those derivatives, etc. You can also learn how to, which we'll do in the next video, that how implicit function can be written parametrically. It will help you to understand a transition in studying in higher dimensional analogs such as this one. And most importantly, the equation, this nabla f of x comma y, it is basically a gradient, and it shows is perpendicular to the curve. And implicit differentiation also helps in to allow you to compute tangent. As you can see, this is tangent and normals are very foundational in differential geometry, as they generalize the tangent spaces and normal spaces in higher dimensions, and that we will see how we move up. So this is the reason, very important, we really understand implicit equation. They are very simple, intuitive shapes. They give you a complete understanding, and they provide a foundation of studying hard dimensional objects. And historically, it connects the classical geometry with modern applications. Now, in the last part of our video, we are also now going to see that from the R2, that is two-dimensional, once we move into three-dimensional surfaces, how things happen and how things look like. Now, all these equations, these are examples of curves in the plane of R2. But what about R3? Now, in the axis, when we talk of the x-axis in R3 is basically given a straight line where y equals to 0. It means no displacement along the y direction, and z equals to 0, which says no displacement along the z direction. So that is what I have written, that this means that y coordinate of any axis must be 0 and z coordinates also might be 0. So if we plot this kind of a value, what we see is that this can go up to minus infinity to plus infinity. X can take any value, and this will also, the point lies entirely on the plane, and what will happen, this will also have a y and a z axis, obviously. So where y equals to 0 and z equals to 0, resulting in a straight line along the y axis. And so y equals to 0 and z equals to 0. So, and as an example in R3 defined by a pair of equations would be this one and this one. So these two are examples of R3, how it is dealt with this equation. Now, obviously, you might have a question that what are the examples of a curve in R3? Well, there are many, but just to tell you, first one is very interesting, which is called a helix. A helix is a very common curve in R3 and can be defined by this equation. So this part is the cylinder of radius r, and this is the linear relation between z and angle theta. So the first equation defines a cylindrical surface around z-axis, and the second equation, z equals to theta equals to 0, this adds a linear variation of z with respect to the angular position in the xy plane, giving the helix. And the intersection of these two is called a helix. Second one is called a circle in a plane. Now, circle in a plane lying in the xy plane can be defined by this. And this is, again, the first equation tells is a circle of radius of r, and this is where plane equal to 0. So this would be that the first equation, x squared plus y squared equal to r squared, defines a circular cylinder extending infinitely along the z-axis. Second equation, z equals to 0, restricts the curve lie to the xy plane, and the intersection is a circle of radius r in the xy plane. So we will pause in today's video there because something we are about to explain which will require a fresh new understanding, which is called a level curve and a level surface, and that we are going to cover up in the next part of the video. So thank you very much for those who have taken up time to watch this video. Please do subscribe to my channel Physics for Students and click on the bell icon to get all the notification from Physics for Students. You can write me and I always respond to this email ID. You can subscribe to my other channel exclusive to x plus y minus also my find by
Alright, I'm not gonna lie, I tried something new. I tried to watch a whole video and then go back and take notes. Because it always feels like it takes way too damn long when I try and take notes during a video or during a simulated lecture, whatever. But this actually was way better. I was actually a lot more engaged, in my opinion at least. Sorry. I was a lot more engaged just now. It didn't feel as long, even though this was probably like, what, 25 minutes to watch it? Probably about 20 minutes. Maybe I spent 30 to take notes on this. But I like this series. It's actually not bad. And I like that they're in like bite-sized chunks, not gonna lie. There's also an intro to topology. There's a bunch of them. This guy's really good. I actually like him. Yeah, and I gotta do this one too, real and complex analysis. Because I need to learn real and complex analysis. So, yeah. What do I even title this lecture? What is this? Video 1 of this series that he's got. Video. I'll say video 1 out of. There's 6 of them. Video 1 out of 6. Oh, okay. Video 01. Alright. That's pretty much that on that. Now I have no clue what we're doing in modern mechanics. I'm so lost, honestly. That may have to wait till tomorrow. I did get some feedback on my research, my physics research. My professor just replied today. I saw it briefly, but that'll be something I do tomorrow morning. Okay, here I think I will put another, and I hope I can do duplicates as long as they're subdivided. Okay, I think I can. Okay, and I'm literally gonna do the same thing but for real analysis. And I'm gonna bookmark this.
On a logically
Yeah, and these are super bite-sized, especially these first couple ones are super bite-sized. So we'll see how many of these we get through. I actually may go back and nah, I'll keep it as video 1. So this one will be video 1, even though I may do like video 01 through, oh, this isn't good. I can only write video 01 once. That's kind of tragic. It's kind of trashy. I'm not really sure what to do. We're just gonna write 1. Alright, next video. This one I think I will, because I have to learn how to write proofs. I will not tell you a lie. That is why I have this. This is the proofwriting course. Yeah, proofwriting course at Stanford. You know, Stanford's on a quarterly? Bless their hearts. Stanford's on a quarter system, so I don't even know what that means. Does that mean they just started? Must be something like that. I think that's what that means. They just started. I think that's what that means. So I think my real analysis assignments, I think I'll get them from MIT. That may be a super stretch, I'm not gonna lie. What book is he using? Is he using Baby Rudin? Probably not. Intro to Analysis by... Okay. Alrighty. Sounds good. Guess that's what we're gonna use. Guess we'll use this book too. I think this should be fine. Full confidence, full speed. And then we'll try some Stanford problem sets if we get there. And this is real and complex analysis, so yeah, okay.
What is real analysis? So if I go by the usual definition, it tells that in mathematics, the branch of real analysis studies the behaviors of real numbers, sequences and series of real numbers, and real functions. Now, this is the technical definition, but to make things easy, real analysis is the mathematics of precision. That means it actually tells how calculus works, not just how you do the calculus. Further, if you see that it tells that real analysis is the branch of mathematics that gives you a kind of a logical and structural foundation of calculus. Also, you can see that calculus teaches you what to do, but real analysis teaches why it works. That means it ensures that every theorem, every mathematics, every equation in calculus stands on a logically unshakable base. So when we are doing calculus, or when you are doing calculus, you deal with differentiation, integration, and further calculations that are involved. But have you ever asked this question, that what really is a limit? Or what exactly do we mean by continuity or infinity or concepts like that? So if you take from calculus, real analysis is actually building calculus from the ground up. That means you actually really now know that why calculus, the concepts of continuity or infinity or limit actually works. So from here, what we can tell is that it answers in definitions that can be proved, tested, and generalized. That means whatever the calculations or the theorems that you have done in calculus, you have taken for granted, it is not like that. It will be much more foundational, much more tested. And what we can say is that calculus teaches you what to do, real analysis teaches you why it works. So that is in a way that you can understand what is real analysis before I go ahead and tell you about the books, procedures, and methods of understanding. Now, here is a quick and a very simple mathematical example which will make you understand the real power of real analysis rather than some vague English definitions. So, for example, if I start with this example, as x gets closer and closer to 2, function of x gets closer and closer to 5. It means that if we plug in the values, for example, x equals to 2, the output comes somehow very near to 5. So for example, f of x equal to 2x plus 1, then this table actually shows that if x goes from 1.9 to 1.99 to 1.999, the value also comes closer to 4.98, 4.998, and so on. So here you can see that as x moves nearer and nearer to 2, function of x moves closer and closer to 5. So in definition, in terms of calculus, we write like this: limit of x tending towards 2, f of x equals to 5. Now, this is a fairly intuitive idea based on the numbers. We get the formula, we plug in, and we score good amount of scores in our calculus examination. But what does closer and closer actually mean? Now, this is where real analysis actually comes in play. How close is close enough? Is 4.9 close to 5? Or what about 4.99999 close to 5? So we need a mathematical way to describe what do we mean by closeness, or something very closer and closer, what do we mean? And in order to do that, mathematicians and physicists have involved two concepts which are called epsilon and delta. Now, I would like to give you a very simple example and translate these two Greek symbols, epsilon and delta, and tell you what actually it means. So when we talk of epsilon, we means that how close we want the output, or for example, to be the limit of, say, for example, L. That means I can tell that you can think of epsilon as our tolerance in the y direction. So if I want, for example, function of x to be within plus minus epsilon, that is the tolerance of L, then we can tell this is the value of the epsilon. Now, what is delta? Delta is how close the input x must be to A to make that happen. So that means that think of delta as the tolerance in the x direction. And in simple language, we can say if x is within plus minus delta range of A, then function of x will be within plus minus epsilon of L. So this is basically what we mean by epsilon and delta. So epsilon is, I will come to summarize that part, but here is a step-by-step idea. You decide how close you want of the function of x to be to the limit of L. For example, within 0.1 or 0.001 or 0.00001. So that is basically the epsilon. So how close you want to be. And then you ask this question, how close must x to be to A so that the function of f of x stays close to L, and that is what is your delta. So from here we can summarize that if such a delta exists for every epsilon, we say the limit exists and equals to L, for example, the epsilon. So the delta definition makes the idea of limits precise, as you can see. It means for every small error, for example, epsilon, you allow in the output, you can find a small distance delta around the input so that the function stays within that error. So simply taking, you can say that if such a delta exists for every epsilon, the limit actually truly exists, and this is how real analysis brings the exactness to our intuitive calculus ideas. So that is how things actually starts into play. So here you can see actually how do we defining epsilon as I want to be close within that range, and delta, if x is within that plus minus delta range, then a function of x will be plus minus of epsilon of L. So from here we can say that real analysis actually it is making our intuitive ideas of calculus much more precise, foundational, and continuous or tending to infinity. These are now rigorously presented in terms of the language of epsilon and delta. So that is why we introduce those concepts. Now, if I want to further test, for example, if I want to test this with function of x equals 2x and a equals to 3, we will claim this one. Now, is this true? Let us say, for example, so if we start with this condition, which is less than epsilon, and we substitute just simply function of x equals to 2x, we get this value. And from here, we can what we can do, if we divide both sides by 2, we get a value of this. So if we select delta equals to epsilon upon 2, then wherever we get this value, we get something which is less than epsilon. And from here, what we can deduce is that for every epsilon, we can find a delta, that is the limit, actually works perfectly. And further, what we can say is that as x goes near 3, 2x goes near 6. And this is actually precise. Nicely written in this definition. Now, this is a set theory definition. I will explain you what this means. So first of all, what does this inverted A means? Inverted A, epsilon greater than 0. It means that for every epsilon greater than 0. So no matter how small a distance you are selecting, no matter, you choose around the value of L, in this case, for example, 6, you can handle it. So inverted is basically a universal quantifier in terms of logic, but here it means that for every epsilon greater than 0. So this is actually what it means. So if I say, for example, if I want f of x to stay within 0.0001 of x and so on. Now, if I take the second one, which is an inverted E delta greater than 0, that means it is again a mathematical term. It tells there exists delta greater than 0. That means I can find a matching small distance delta for x, so that this actually happens. So you can again say delta is like your input tolerance, how close x must be within the target point of 3. The next part, again, it is a set theory such that if means actually x is close to 3 but not exactly equal to 3. That means you're looking at points near 3, nor not right on the top of it. Then 2x minus 6 is less than epsilon. That means the output value 2x will be close to 6 within your tolerance. That means that if I take this kind of an pictorial understanding, then no matter how tiny a band, for example, epsilon, you draw around the number 6, I can still find a band around 3, so that whenever x stays within delta to 3, 2x will also stay within epsilon of 6. Now, if I go back, here you will now see that this definition is clear. For every epsilon greater than 0, there exists a delta which is greater than 0 such that so and so the conditions. So I explained you those set theories in simple English so that you can understand. So 2x minus 6 less than equals to less than epsilon means that how small a band, for example, epsilon you put around 6, you can still find a band delta around 3 so that whenever x stays within that delta of 3, 2x also stays within epsilon of 6. So from here, what you can tell simply is that epsilon means how close do I want to get to the answer, and delta means how close do I need to be the input to make that happen. So as x moves close to 3, function of x moves closer to 6, perfectly controlled by epsilon and delta. That actually confirms the notation that x tending towards 0 to x equals to 6 with precision. So this is basically, I would say, in a way, how we are actually defining closely the value of limit and near and close and so. So that is how real analysis actually transforms the word approach or approaching into a kind of a probe. The question remains that in spite of all those understandings, is there any practical implication? Because I have seen most of the students telling that real analysis is a very dry subject. It is based on pure mathematics. It has got hardly any application. So why should we learn it? Definitely, at the first go, real analysis looks just like complicated symbols. But it would ask you, or you can ask yourself this question, why actually calculus works? That means if you're learning calculus, you learn how to differentiate, how to integrate, how to find limits. But real analysis gives answer, what exactly is the limit? When does function really have a derivative? Or why does this formula works in this way and that way, and why they do not fail? So calculus and real analysis in some way are all related to quantum mechanics and quantum physics, which are related to continuity and convergence. So real analysis is what makes those ideas. You can take an analogy telling that if calculus is basically driving the car, then real analysis is basically the engine. It tells how the car actually works. Now from here, I can tell that real analysis is closely related to physics, because real analysis provides a rigorous foundation for understanding continuous change in space and time, which is essential for solving physics laws. It is also related to engineering because it ensures precision in modeling signals, systems, optimization problems, where accurate limits and convergence determine stability and performance. Also in computer science, it underlies algorithms for numerical computations, machine learning, graphics guaranteeing their continuous process can be approximated and analyzed effectively. So remember that it is absolutely not a useless abstraction. It is the grammar of mathematics. So for example, if you know the grammar well, you can pick up any language easily. So real analysis actually tells you how to calculate. So if it is a comparison without real analysis, it is just a formula. You accept that it is infinite. You just draw curves. But with real analysis, you prove when they work. You know how to test convergence rigorously, and you can define continuity and limit and smoothness, actually what they mean. So this actually gives you an understanding the power, the real usage, and in terms of using real analysis really. So practically, if someone wants to go beyond applying formulas, then you need to understand real analysis. Also, real analysis is something which builds your mathematical muscle. Why? Because it trains your brain in a rigorous logical thinking, which you have not done in calculus. You have just assumed and you have plugged in the formula and you got the results. So writing proofs actually improves structured argumentation. You can understand these concepts, and logical rigor sharpens your analytical reasoning, coding, and policy modeling. So all in all, what we can see is that real analysis is what ensures that the mathematics we use in science, technology, economics, or whatsoever works reliably, precisely, as well as predictably. Move to the next part, which is what are the mathematical prerequisites required for mathematics? Well, you need to know what are called algebra and inequalities, because you should be comfortable with these kind of expressions, which you can see right on the screen, because real analysis constantly deals with absolute values, inequalities, etc. You should be aware what this mean by less than epsilon, etc. The second point is functions. You need to know functions and graphs, because without that, you won't be able to understand what is a domain and range, inverse function, composition of functions, and so on. So in real analysis, you need to study properties of functions, continuity, monotonicity, boundness, all these things. So a very good understanding of functions and graphs would be the second prerequisite. Third would be obviously basic set theory, because the entire part of notations are written in set theory. So union, intersection, quantifiers, all these things would be required, because real analysis is written in the language of logic. So this type of statement which I have just shown you should be familiar with. Yes, sequences and series from calculus should be clear, because you need to know what do we mean by sequence, when does it converge, etc. Why? Because much of real analysis starts with what do we mean by convergence, numbers, sequences, and so on. And the fifth would be coordinate geometry, because that is something which is very intuitive: slope, derivative, area under the curve, and these are required because this would come intuitively for formal proofs, so that you do not feel it dry. Mathematical proofs and reasoning, I've already made a video on the sheer importance why you should have an understanding of mathematical proofs. It is important. This won't come in a day, so you have to really practice, because real analysis is completely a proof-based subject. Each theorem, each equation, you need to go ahead and prove it. And that is why from calculus you move to real analysis. You prove those theorems and understand the power and the beauty of that. So coming to the main core idea of this today's video, what is the best book to start for real analysis? There are many books in Amazon, and if you search in Google, that is Amazon review that functions. This is one of the best book to start. I will just tell you how sets are giving you an idea of sets, statements, and function. Because this is the grammar. So here you can see I've just taken screenshots of few of the what do we mean by set, functions, etc. So you go ahead and understand what is a composite function, inverse functions, and binary operators, symbols like this. All of real analysis, continuity, limits, differentiation are properties of function. So the first chapter actually builds the language of symbols, and you need to understand that. This is a screenshot of 1.1 to 1.9. Page numbers I have not given. These are this is quite a dense book, I think around 600 plus pages. So these are sets and functions, statement, connectives, etc. First step, obviously, how the real numbers are, and you already know that square root of 2 is something like that, and it is an irrational number. It cannot be expressed in this term. So in order to express those things, we need to have new set of numbers which fills up the gaps, and that is what the real numbers do. They make the number line continuous and complete. So the concept of bounded supremum, infimum, all those things come in play. And this is the second most important step. Now, why it matters? The reason is that completeness of the real number ensures that every Cauchy sequence actually converts to a real number. I'm not explaining this is a technical part, but this is the backbone of real analysis. How we build the construct, how we construct the real number lines, that is important. And here you can see a very exhaustive contents given in terms of understanding real analysis or the real numbers, starting from introduction to objective question. This is step number 2. Third step comes once you know what is the real number line, you go ahead and understand neighborhoods and limit points. So the idea of closeness in calculus is now being rigorously explored. So you need to understand, for example, if I take this kind of a simple example, a neighborhood point of A equals to 3. So if it is 0.1, the neighborhood is between 2.9 and 3.1, and so on. So why it matters? Because these ideas define continuity property, this definition. And the limit itself is defined by this. So that is why you see all the symbols, etc., will come in play, and you need to go first chapter. If you don't understand the symbols of set theory, you won't be able to proceed that. So this actually means that by taking x close enough to A, we make function of x as close as we want to function of A. This very simple mathematical language. So this is again the heart of real analysis. Again, you can see a very exhaustive table of contents, closed sector, and it actually tells that some infinities are bigger than others, and it explores finite, countable, infinite, etc. So for example, if I take set of natural numbers n equals to 1, 2, 3, dot, 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 so on, then we say it is countably infinite. We can list them in order. So the set of real number is uncountable. That means you can list all real numbers. You cannot list all real numbers which lies between 0 and 1. And that brings us to the famous Cantor's paradise, the famous mathematician George Cantor. This is the Cantor argument, shows that between 0 and 1, no matter how you list the decimals, one number will always be left out. This is being explained in the book. So real numbers are actually much denser than rational numbers, and there are infinitely many rationals between any two reals, but still the reals form a bigger infinity. So 0.1, 0.11, 0.1, and infinitely more exists. So here the book actually prepares you for studying the next step, which are called the continuity and limits. And here I have given again a screenshot of what is covered in terms of countability of sets. And then, as I have shown you, if you turn the page over here, this is actually a precursor to continuity and limits. And the next chapter talks about sequences, the foundations of limit and continuity. So you know what is a sequence is, A1, A2, and A3. So real analysis actually studies, it asks this question: as the index n becomes very large, does the sequence at all approach a limit? So for that, we have different kinds of convergence. sequence, it settles down the single value. Divergent sequence, it grows without bound, and so on. A sequence where terms get closer to each other is called a Cauchy sequence. And then we have got monotonic sequence which increases towards 1. So overall, sequence is definitely a backbone of analysis. They define limits, continuity, even integrals. And this chapter actually teaches you how to test, most importantly, prove and reason about convergence. So the sequences are this: sequence, bounded limits. Again, this is the next step, building the complete understanding of this sequence. Then comes what are called infinite series with positive and negative terms. So here the book again takes a big step, that is infinite summation. You know what is an infinite series look like. So from here we ask this question: does this infinite sum approach a finite number? And then again there are simple examples like each term gets smaller and the total approaches 2. This grows without Brown, that is the harmonic series. Then the D'Alembert ratio test, the series converges and so on. So series are everywhere in mathematics that we find. I mean to say, this is undoubtedly very important. And understanding why a series converges or diverges gives a analytical control, and you can understand the infinite process. Here again, you can see quite a detailed, exhaustive understanding of these chapters. Into the parts of the table of contents. It's a very exhaustive book, and it gives you a complete understanding of how to go ahead with the understanding of real analysis. So you can, it's a book review of the book. It is under 80 book cover. It doesn't cumulatively decline it analyst per pound. Please do not forget to subscribe. Hello everyone.
Alright, that's it. I'm gonna stop there, and tomorrow morning I'm actually gonna pick back up with this video and take notes over the first, like, all of this. Yeah, to like here. Once he gets here, I feel like it's a promotion. I'm not gonna lie, just a promotion. But from here and back, and then I'll look into some of these questions and see. So, yeah.